Hello everyone, this is Dr. Lennon, and today we're going to talk about antiderivatives. So what's the basic idea? Well, let's start with the definition and go from there. So given a function f of x, which we'll denote by lowercase f of x, we say a function capital F of x is an antiderivative of f of x, provided when you take the derivative of the big function, capital F of x, you get the lowercase f of x. So let's just think about an example. So what is an antiderivative of, let's say, little f of x equals x squared? Now, that's a question, sorry. So we remember from taking derivatives, we really understand how the pattern of derivatives with respect to polynomial functions, right? What does it do? It brings down the power in front as a multiplicative factor and then decreases that power by 1. Now, the way the antiderivative is defined is it's actually going to be essentially the reverse process, because now we're looking for something such that when you take the derivative, you get the thing in question. So you might take a stab at this one and say, well, I know the derivative decreases the power by 1, so I know that the power would have to be 1 higher. So you might guess first and just say, okay, maybe it's capital F of x is equal to x cubed, but then you could take the derivative and see, well, that would actually be 3x squared, so that would not work. So then you make an adjustment, and you say, well, there's this 3 in front, so if I just divide the answer by 3, what will happen? So if we say instead f of x equals x cubed over 3, then voila, we see f prime of x is equal to 3 times x squared over 3, which just becomes x squared. So this one, in fact, works for us. So we could say that capital F of x equals x cubed over 3 is an antiderivative of x squared. So we found an antiderivative there. A follow-up question, though, is we're saying, think about the article we're using. We're saying and, so that implies that maybe it's not unique. So a follow-up question might be, is this the only antiderivative of x squared? So, you may want to pause your video here and think about that for a second. But pretty quickly, hopefully, you should realize that the answer is no. There are certain things that when you take the derivative of, they just vanish, namely constants. So, so if we said maybe, what about consider capital F of x equals x cubed over 3 plus 7? Then you still have f prime of x is x squared. So the takeaway here is adding or subtracting any constant won't affect the value of its derivative. So for this reason, we would call, so f of x equals x cubed over 3 plus c, where c is any constant, that is going to represent all antiderivatives of x squared. So this represents what we call the family of antiderivatives. Of x squared. So when we add that constant, this is known as the general antiderivative. So I will introduce some notation. There's some notation that relates to the notation we had for Riemann sums. So what is that notation? If we write the integral of f of x dx, so this is known as the indefinite integral of f of x. And basically what it means is to find the general antiderivative of f of x. So, and yeah, it means find the general antiderivative of f of x. So I probably could have worded that a touch better, but I think you get the idea. So there's different names for all the parts of it too. The elongated S-looking shape is just known as the integral. F of x, the function being integrated, is the integrand, and d of x is the differential. So that would play more of a part. This is kind of the limit of that sum that we're talking about. And we're not going to talk about formally applying the limit to a Riemann sum to get the integral, but that's essentially how it works. We're going to focus more on just computing these antiderivatives in this lecture. So let's try to find antiderivatives for polynomials. Polynomials have a very regular behavior with their derivatives, so hopefully their antiderivatives will follow some pattern as well. So let's look at antiderivatives of polynomials. So we'll do this kind of in a couple parts. So the first thing we'll look at is constants. So one, we'll just look at constants. Those are the simplest of all polynomials. So if you would have something like, a little f of x is just equal to, say, 5, you would have to think, what function has derivative 5? And then you might quickly realize, well, one such function is 5x. So if we want to frame that in terms of the general antiderivative, so the general antiderivative of 5 must be 5x plus c, where c is an arbitrary constant. So with our new notation, what would that look like? We could say, well, the integral of 5 dx is just equal to 5x plus c. So that's how it would look with the new notation. You might just be tasked with computing the value of that indefinite integral, and then that would be your answer. So this gives us a general formula. So the more general formula is for any constant. So generally, for any constant k, if you try to evaluate the definite integral of k with respect to x, you would have k times x plus a constant. So there, k is just playing the part that 5 did in our numerical example. So for any constant, the antiderivative is just kx plus c. That's the general antiderivative. So then we might look to, after that, let's just say, what about maybe linear functions? So even simpler than linear functions, we could just think about what is the antiderivative of, so actually, no, I didn't want to think about linear functions. I wanted to state one thing. So there's one small exception to this. There's one constant that is not going to have antiderivative kx plus c. Well, it kind of does, but so let's note further. Note that if k equals 0, the antiderivative is actually just a constant, right? What does this amount to? The antiderivative of just 0, well, it would be 0 times x, which is 0, so we actually just get a constant. So we have no x part there. So 0 is kind of a special case for these constants. So actually, we don't need to worry about linear functions quite yet. Let's just think about maybe the general way. So let's think about just more generally polynomials. So let's move on to polynomials. So let's look at a single term. So let's consider first single term, i.e. monomials. So really that's all we want to think about is what if we want to find the antiderivative of let's just say some random power of x, say maybe x to the 4th. Well, we already did it with x squared, and we realized that the power had to be 1 higher, so we know that this is going to be something like x to the 5th. But if you take the derivative of x to the 5th, you would get 5x to the 4th. So you have to adjust for that factor in the bottom. So we know basically, so the antiderivative with constant equal to 0 would be x to the 5th over 5. So so the general antiderivative here of x to the 4th dx is x to the 5th over 5 plus c. And we could do this with other powers, right? We could say, e.g., find the antiderivative of x to the 12th. And again, the general antiderivative, when you're looking at this power, what are you doing? We know the degree has to be 1 higher, and then if you took the derivative, the 13 would come out in front, so we have to divide by that number instead to compensate for that. So what we'd like to do is we'd like to make a general formula. So we would say find the antiderivative of, let's say, x to the n. So what would that be? Well, it's the same process, right? We know that the power has to now be 1 higher, which would be n plus 1, and then we're always dividing by whatever that number happens to be. Okay, so yeah, that basically takes care of all single term polynomials for us. So some useful things to know, some properties of these indefinite integrals. So so properties of the indefinite integral. So there's many, but I'm just going to use 2 right now that will allow us to extend to general polynomials. And basically, let's look at, so we have the constant out rule. that says if you have the integral of some constant, let's say k, times a function f of x, well, what you can do is you can just take out the k in front and then do the integral of the regular part of the function like you typically would. So how could we make light of this property? Well, let's look at, say, the integral of maybe 7x to the third. So what we can do is we can take that 7 out front and then just ask ourselves, well, what is the indefinite integral of x to the third? And we know that that is going to be 7, and then we would know the antiderivative here would be x to the fourth over 4 plus a constant. Now, if you would want to write this out, we could say, okay, this is 7x to the fourth over 4, and then you might say plus 7c, but because c is a number representing all constants, you actually don't need to write 7c because you can just replace 7c by c, because if you take all the numbers and multiply them by 7, you still get all the numbers. This is a common trick when you're dealing with arbitrary constants. So we would actually just write 7x to the fourth plus c. So normally you would kind of exclude these two middle steps. Basically, the thing to note here is since c is arbitrary, then 7c is arbitrary. Okay, so that kind of highlights the constant out property. The second property is the additivity. So this basically says that the integral of two functions, we can look at their integrals separately and do them one by one. As you can imagine, this isn't going to work with multiplication. Remember, for derivatives, additivity and differences worked very nice, but the same was not true when we tried to look at multiplication and division. So, for instance, here we could look at, sorry, I'm just wondering how I wrote it up here. Yeah, so if we looked at, say, the integral of x to the third plus x to the fifth, well, what we can do is we can just do each one separately. So x to the third dx plus the integral of x to the fifth dx, and we get each one on their own. So we get x to the fourth over 4 plus x to the sixth over 6. And when we only need one arbitrary constant, again, we could write down two of them, but adding together two arbitrary numbers is the same as just including a single arbitrary value. So let's go ahead and just do a couple more of these, but again, they're kind of as expected. So I'll just say compute. The notation tells us exactly what we're trying to do. So that's one reason it's nice and efficient. So let's look at the general antiderivative of 15x squared plus 10x minus 9 dx. And basically what you're doing is you're just looking at this term by term. So I'll write out that we're using the additivity property to separate them into three separate integrals. But typically I would never write this step. So again, the minus sign we can think of as a constant as well. So really, we can just think of subtracting 9 when we're doing the antiderivative. So what do we get here? Well, we get 15x to the third over 3 plus 10x squared over 2 minus 9x, and then we just need one arbitrary constant, and then we can simplify some of those numbers. So we get 5x squared plus 5x cubed. Sorry, I was looking ahead. 5x cubed plus 5x squared minus 9x plus our constant, and that's it. So let's look at another one. So let's say we're integrating maybe 8x squared minus 5x over x dx. Now, again, this doesn't quite look like a there's a quotient involved, so don't try to jump the gun and just take the integral of the top and the integral of the bottom separately. We have to apply some algebra to make this look like a polynomial first. So this is going to be the integral of 8x squared over x minus 5x over x dx. So really that's all we're looking at here is the integral of 8x minus 5. It was just sort of in disguise. And then that's not so hard to do. That's going to be 8x squared over 2 minus 5x plus a constant. And then we can simplify the 8 over 2. Just change that to a 4. So we get 4x squared minus 5x plus our arbitrary constant there. So that's it for computing the antiderivatives of polynomials. So next time what we'll do is we'll look at finding antiderivatives of other classes of functions, mainly logarithmic functions and exponential functions, the primary kind of classes of functions we work on in this class. So this is Dr. Lennon signing off.